This is the second video about the best methods for oxidizing secondary alcohols to ketones. In this video I'll show you some procedures based on the use of hypochlorite as oxidant. If compared to hydrogen peroxide, hypochlorites have the advantage that the product will not be transformed into an explosive peroxide. Moreover, hypochlorites do usually not bring about any Baeyer-Villiger type oxidation, but can chlorinate the product and cause chloride-induced corrosion of the reaction vessel. The oxidation of alcohols by hypochlorite can proceed by two different mechanisms. The chlorination and oxygen of alcohols by hypochlorites is a very fast reaction, as illustrated by the organic synthesis procedure for the preparation of terzbutyl hypochlorite from terzbutanol. The chlorination is almost a titration and is finished as soon as the hypochlorite has been added to the reaction mixture. If the resulting organic hypochlorite has a hydrogen atom in alpha position, elimination of hydrogen chloride and formation of a ketone can occur. This, however, is not the normal way in which alcohols are oxidized. Most oxidants abstract the alpha hydrogen atom as hydride, not as a proton. Accordingly, a second mechanism would be the direct hydride abstraction from the alpha position by hypochlorite or hypochloric acid. Since bases and hypochloric acid are involved, the rate of both mechanisms is probably highly pH dependent, as well as on the precise acidity and structure of the alcohol. Even the solvent and the way the reaction is conducted may have an impact on the mechanism. The main advantages of hypochlorite as oxidant are its low cost and that only sodium chloride is produced as byproduct. Furthermore, the reaction seems to be sufficiently selective to allow the oxidation of secondary alcohols without affecting primary alcohols. Similar as with hydrogen peroxide, some lipophilic alcohols may require a biphasic reaction mixture and the use of a phase transfer catalyst. Then, in order to avoid chlorination of the product, only a slight excess of hypochlorite should be used, or even less than one equivalent if chlorinated byproducts are more difficult to separate from the product than unreacted starting material. Because the quality of commercial hypochlorites is quite variable, their strength should be determined by titration. A further disadvantage is that, unlike hydrogen peroxide, chloride can cause the corrosion of steel reactors and other metallic equipment. In this example, menthol was oxidized with calcium hypochlorite in aqueous acetonitrile. The yield was very high, also because chlorination of the menthol group would probably require a higher reaction temperature. This example is similar to the previous one, the only difference being that the oxidation was conducted in pure acetic acid. Again, the yield was very high for this ketone devoid of sensitive functional groups. The oxidation of secondary alcohols by hypochlorite is usually performed under slightly acidic conditions, under which hypochloric acid and chlorine can be formed. Both are strong chlorinating reagents, capable of chlorinating ketones and many other functional groups. Therefore, the most important potential side reaction is the chlorination of the product. Ketones readily react with chlorinating reagents, even under mild conditions, and it is therefore important to avoid an excess of hypochlorite. Although chlorine and hypochlorite are among the least expensive oxidants available, a number of closely related reagents have also been used for the oxidation of secondary alcohols. These include trichloroisocyanuric acid and a number of brominating and iodinating reagents. Some of these are easier to dose accurately and may be more selective than hypochlorite, what can be beneficial for structurally more elaborate starting alcohols.